Alright guys, here we are with section 3.3, properties of logs. What we should be learning today: using the change of base formula to rewrite and evaluate logarithmic expressions. Use properties of logs to evaluate or rewrite logarithmic expressions. Use properties of logs to expand or condense logarithmic expressions. And use log functions to model and solve real-life problems. So the change of base formula, probably one of the more important things from today. Most calculators have only two types of log keys: the common log, LOG, which is base 10, and the one for your natural log, base E. I know we looked at it yesterday, and some of you guys with the 84 Plus color edition, you were able to get in there and actually do a different log, change your bases. Okay, but even that can be a little bit of a time-consuming pain. So sometimes this is just as easy to use this. Okay, so if you're changing it to a different base, alright, the number that's already big, so like log base A of x, whatever you're changing it to, your new base, say you're changing it to the new base of B, log base B of x on the top, and then log base B of what your old base used to be, A. If we're changing it to base 10, because that's what your calculator is probably going to be able to do the quickest, that should have its own button on the top, or the main screen there. So if you have log base A of x and you want to do it quickly without having to go through a bunch of menus to try to find the change to the custom base one, you can just do log base 10 of x divided by log base 10 of A. How I remember that is that the big one goes up and the little one is already, it's subscript, it's already down a little bit, that one's going to go on the bottom. And you can do the same thing with natural log, log base E. One way to look at the change of base formula is that logarithms with base A are simply constant multiples of logarithms with base B, the constant multiplier being 1 over log base B of A. Okay, let's see this in action. Let's do some problems. Okay, so log base 4 of 25. Yes, I know some of you know how to get in there and get to the spot in your calculator where you can actually do the log with base 4 of 25. But like I said, that can kind of be a little bit of a pain to get into that menu and get there and do all that, when just from the main screen we can do common log, or log base 10 of 25 divided by log 4 pretty quickly. Okay? And we should be able to get 2.3219 about. Okay, so we got log 25, close your parentheses, divided by log 4. 2.3219, yep. Okay, so probably a lot quicker, or just as quick, it's definitely not slower, than scrolling through all those menus to try to find the spot where you can change the base. Okay, let's give you a second here to try this one. Alright, hopefully we're able to type that into your calculator pretty quickly, and we should be getting 3.5850. Log 12, close them, divided by log 2. That last spot rounds up, makes that a 0, makes that a 5. 3.5850. we know that the logarithmic function with base a is the inverse function of the exponential with base a. So it makes sense that the properties of exponents should have corresponding properties that involve logs. For instance, the exponential property a to the 0 equals 1, anything to the 0 power equals 1, has the corresponding log property, log base a of 1 equals 0. Or if we were to turn that around, 0 is the power of a that gives me 1. So we're going to have a bunch of matching properties. And here they are, properties of logs. We got the product property. So if we have log base a of u times v, we can separate those into two separate logs, both of base a, with addition, whether you're using common log or natural log. Quotient property, log base a of u divided by v, we can separate those into two separate logs with subtraction. And then the power property, log base a of u to the n power. That n, when you're doing logs, can come down in front as a multiplier down in front of your log. Okay, and we can do that with natural log as well. So those are in your book if you need any more time, or I'll try to get handouts printed up for you guys so you have these. Okay, let's change these into terms of natural log, just using natural log of 2 and 3. Alright, so the first one, piece of cake, 6, could be rewritten as a 2 times 3. And then I can separate those out with the product property, natural log of 2 plus natural log of 3. And that's as far as I want us to go, not actually type those in. If you're going to type it in, you could have just typed in natural log of 6. Okay, what about this one? Division. So we can separate those out with subtraction, natural log of 2 minus natural log of 27. Done, right? Not so fast. We want all 2's and 3's. 27. That is going to be natural log of 3 to the 3rd power. And then we can use our power property to bring that 3 down in front. So we'll have natural log of 2 minus 3 times the natural log of 3. Tricky, tricky. Make sure we're following those directions. Too easy just to write that down as a subtraction. Okay, next one. Find the exact value of each expression without using a calculator. Use your brains. Okay? So these should have some pretty quick little tricks to them, right? Alright, look it over here. Natural log of e. Okay? Natural log is the inverse of e. Boom. 12. Boom. Plus 5. 17. Alright, let's see if you can think about this one for a little bit. Okay, first hint. Change that root to a fraction exponent. Alright, I'll give you about 10 seconds here of a head start. Okay, so if I change this root to a fraction exponent, we're going to have log base 7 of 7 to the 1/5 power. I can bring that 1/5 power down in front. And log base 7 of 7, that was one of our properties from a previous section, section 2 or section 1 here, by section 2. Log base 7 of 7, what is the power of 7 that gets me 7? 7 to the 1st power, so we got 1/5 times 1, or just 1/5. Piece of cake. The properties of logs are useful for rewriting logarithmic expressions in forms that simplify the operations of algebra. This is true because these properties convert complicated products, quotients, and exponential forms into simpler sums, differences, and products. Let's take a look. Log base 4 of 5, x to the third y. Boy, that looks intimidating, doesn't it? Okay, but we can use our log product property to separate these out into less intimidating pieces. So we're going to have log base 4 of 5 plus log base 4 of x to the third plus log base 4 of y. Okay, don't forget about your power property. We can bring this little 3 down in front of just this one. 3 times log base 4 of x plus log base 4 of y. A lot less scary when they're all split apart. Okay? Well, what about our next one? So we can separate division out as subtraction. Minus natural log of 7. Okay. Remember that the square root is what power, what fractional exponent? That would be the 1/2 power. So we're going to bring that 1/2 down in front times natural log of 3x minus 5 minus natural log of 7. Not too bad. Oop, got a little tipped sideways on you. Sorry there. Okay, let's see if you can go in reverse, putting them back together. So far we've been peeling back the onion. Ogres are like onions. So many layers. We've been peeling back the layers. Now we're going to put it back together. Okay? So I'm going to walk through the first one here with you, and then I'll give you a minute or two on your own to get B and C going. So we have this 1/3 multiplier in the front. That's telling me I can put that back up here. 5 multiplier going up here. So we're going to have log of x to the 1/3 plus log of x minus 3 to the 5th. Okay, and then we have addition, and I can put those together with multiplication. And a lot of the times, I don't care if you're going to leave the 1/3 up there, but a lot of the times the book will just go with a cube root. So if I was going to be like the book, we're going to have the cube root of x times x minus 3 to the 5th. So that's what the book will usually do. I don't care if you leave it as x to the 1/3 times x minus 3 to the 5th. Up to you. Alright, let's give you a minute or two to try to put these two back together. We got subtraction. We got multipliers out in the front to take care of. Got addition here with a multiplier in front for the whole thing. Okay, let's see here. So we bring that 4 up, 2 up, and then it's subtraction, so we're going to combine those with division. So we're just going to have one big natural log of x minus 4 to the 4th over x squared. And then with this one, we're going to put them together with multiplication. Okay, we're going to put them together with multiplication. X times x minus 2. And then we're going to take that 1/5 up on top of everything. Or like I said, the book will usually change that to a root at the end. So we have log base 3 of the 5th root of x times x minus 2. Okay. Next up we have application. Real life problems. One method of determining how the x and y values for a set of nonlinear data are related is to take the natural log of each of the x and y values. If the points are graphed and fall on a line, then you can determine the x and y values are related by the equation of natural log of y equals m times the natural log of x, where m would be the slope. So we're taking some nonlinear points. Okay, we're going to do the natural log of all of them, and then sometimes they will all work out there to be linear after you do your natural logs. The table shows the mean distance from the sun, x, and the period y, the time it takes a planet to orbit the sun, for each of the 6 planets that are the closest to the sun. In the table, the mean distance is given in terms of astronomical units, where Earth's mean distance is defined as 1, and the period is given in years. Find an equation that relates y and x. Okay, so if you look at the next slide, you can kind of see here that it's not completely obvious as to how they're related. These are all really close together, and then we start getting big jumps, right? We start getting big jumps over here with Jupiter and Saturn. So it's like, I don't know, is it a straight line like this? Is it more like an exponential curve up there? What do we have going on? Okay, to solve this problem, take the natural log of each of the x and y values in the table, and then your new table would look like this. And then I'm just going to put the book up there. This is example 7. And from your natural log points, your new natural log numbers here, this is actually going to have a linear relationship. By plotting the points in the second table, you can see all the points appear to lie on the same line. Okay, so here's the book part of it. So after we do that, the natural log of all the points, it does make a straight line, and we can come up with an equation in terms of natural log. Y equals 3/2 or 1.5x, where capital Y is the natural log of little y, and capital X is the natural log of x. So we can conclude that little y would also be equal to 3/2 the natural log of x. Natural log of little y equals 3/2 natural log of x. This is more of like an awareness type of thing, that just be aware that you can do that. As far as a quiz and a test, I'm not so sure that that would be a major focus. The major focus is more going to be on the properties and being able to use those properties from the table. But alright guys, there you go. Looks like you're going to have plenty of time in class today to get a start on your homework or on those online quick checks. Okay, thanks for watching. We'll see you next time.